This is done, at least in R3, using the cross product. So we use a very specific notation. The vectors I, j, and k, they represent the canonical vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. So you can write any vector in R3, x, y, z, as an inner product, except it's not really an inner product, right? If you think about it, I wanted to tell you, oh, this is going to be simple. We can write this vector x, y, z here as, well, basically x, y, z times I, j, k. But if you think about this, I mean, formally this would be this object times this object plus this object times this object plus this object times this object. So yes, I mean, formally this is the same expression. But this doesn't really make sense, right? Because this is a point or a vector in R3, and this is what? This is a combination of 3 vectors in R3. So this belongs to, I don't know what it belongs to. Can't really write it this way. This is more a linear combination of the vectors I, j, and k, where the scalar, the coefficient associated with them would be x, y, z. Now, even though I told you you can't really do this sort of fancy footwork because some of these things are vectors and some of these things are scalars and they don't sort of like play well together, we're still going to use a notation that uses that false expression. I mean, we're going to use it formally without really thinking about what it means, because if you think about what it means, it doesn't make any sense. But if we just blindly follow the instructions, it does make sense. So it's sort of like a shortcut or a recipe. It doesn't mean what it typically means. And the notation we're going to use is the notation of the determinant. This is something we'll discuss in excruciating detail when the time comes to talk about matrices and invertible matrices. In R3, the cross product of 2 vectors, u and v, is a new vector. U dot v, the inner product that was a scalar, cross product u times v, it's a vector. So this thing here is also in R3. And what's the vector? Well, this is a formula that most of us have a real hard time remembering without using the shortcut notation. You take, for the first component of that new vector, the second component of the first times the third of the second vector minus the second component of the second vector times the third component of the first vector. So yz prime minus y prime z. And then for the second component, you use x prime, the first component of the second vector minus the third component of the first vector, times the third component of the first vector minus the first component of the first vector times the third component of the second vector. That's the second little bit. And finally, for the third component of this new vector, it is the first component of the first vector times, it's like, oh, okay, it's way too complicated. Who's going to remember this? Very, very weird notation. It's easier to make sense of this if we remember u cross v using this notation. The vertical lines here mean that we're going to be computing something like a determinant. I'm going to take the time to spell it out properly here for you. Sorry, let me write it out here. Okay, I haven't yet defined what the determinant is, but I'm going to explain to you what this notation is saying. So the bit that is here, I, j, k, these are vectors. Then we have x, y, z, and then x prime, y prime, z prime. It works this way. You start with the first entry in the first row, which in this case would be an I. So you'll have I times something. And then you subtract the second one. So minus j times something. And then you add the third one. So that's k times something. All right? So the first thing to remember, you go along the first row here, and you're going to have plus I minus j plus k. So alternate 1 minus 1, 1. Okay. What is the rest that goes in here? Very easy to remember. If you picked I for the first row here, you're going to remove the rows and the columns that correspond to I. And you are left with what? You're left with the determinant. So let me make these lines here straight. Y, Z prime, Y prime, Z. Let me repeat this. You look at what term went in here. It was the I, and you remove the rows and the columns in which that I is found, and you're left with a 2 by 2 array. If you do the same thing with J, and unfortunately I actually scratched this one out and I don't want to delete it because it's going to delete everything, but if you do the same thing with J, you're scratching out the row that contains the J and the column that contains the J. And so you're left with X, X prime, Z, Z prime. So let's put these in square lines as well. So X, Z, X prime, Z prime. And for the last one, the K, you scratch out the row that contains the K, and you scratch out the column that contains the K, and you're left with these things. Now, these straight lines over arrays mean something very specific. It's sort of this mixed product. So how do I compute the determinant, the straight line of a 2 by 2 array? Very easy. I multiply together the elements on the diagonal, so y times z prime, and then I subtract from that the product of the elements on the, let's call it anti-diagonal or the counter diagonal. And that's going to give me y times z prime minus y prime times z, which is exactly what I get here. I times this, well, what is I? I is the vector 1, 0, 0. This determinant here is a scalar quantity. It's a number. And I have a number times the vector 1, 0, 0. It only affects the first component. It doesn't affect the other two. I do the same thing for the other ones. If I do the determinant, I have x times z prime minus z times x prime. And I multiply that by the vector j, which is 0, 1, 0. But remember, we had a minus in front of it. And so I'm going to get this bit here with the signs reversed from what you would have expected. And you do the same thing with k. Now, you might have other tricks to remind you how to compute the cross product. I've shown you one. This one is useful, especially when we eventually start talking about determinants, and it's all going to be like natural then. So it's not a bad idea to start learning it this way because it provides you with the right way to think about determinants, and we introduced that early on. So this result is a new vector in 3 space. And for instance, if we were trying to compute the product or the cross product of 1, 2, 3, and 4, 5, 6, we would place them in the array here. We're trying to compute the determinant, ijk 1, 2, 3, 4, 5, 6. I can just use the formula that's here. It's very straightforward, and I would get minus 3, 6, minus 3. Don't just take my word for it, especially if you've never computed these things before. Pause the video and go and make sure you get that vector. If you instead multiply together 4, 5, 6, 1, 2, 3 using cross product, you're going to get, well, a vector that looks very much like the first one, but that is not equal to the first one. Instead of minus 3, 6, minus 3, you're going to get 3, minus 6, 3. What we get out of this is that the product of these two vectors is actually minus the product of the other three vectors. You see here what's happening. The cross product is not commutative. The order in which you multiply the terms actually has an effect on the outcome. But one thing that's very important for you to notice is that if I take the first vector, 1, 2, 3, which was the first vector in that example, and I do the dot product with the outcome, with the cross product, then I get 0. And what that means is that 1, 2, 3, the first vector, is perpendicular to u cross v. And I do the same thing with vector 4, 5, 6. 4, 5, 6, dot product with the cross product, 3 minus 6, 3, I also get 0. So 4, 5, 6 is also perpendicular to the cross product. In general, that's always going to be the case. If you have u and v, the cross product of u and v is a third vector which is perpendicular to both u and v. There are some properties here for us to look at. If you have three vectors in R3, then first of all, they are anti-commutative. In physics, that's going to end up playing a role, especially when you talk about elementary particles and symmetries. It's very interesting. So u cross v is minus v cross u. Not the same, but also not completely different. If you multiply u dot product with the cross product, you get 0, same as if you were to multiply u cross v dot product v. And that's because u and v are orthogonal, perpendicular to the cross product u times v. The cross product is distributed, or gets distributed with respect to addition. So u plus v times the cross product would be u cross w plus v cross w. Say that there's a distributivity here. And there's a formula for the length of the vector u cross v. It is the norm of u times the norm of v times the sine of theta, not the cosine. So it differs from the norm of the, or the magnitude of the dot product. Let me remind you the formula for the dot product. This dot product would be length of u, length of v, times the cosine of theta, right? Now this thing could be negative. It's conceivable because cosine of theta could be negative when theta goes from 0 to pi. But sine of theta is always non-negative between 0 and pi. And so this quantity here is always positive. This sum is in fact the area of the parallelogram that has u and v as sides. The area here would be this quantity, where the angle between them is theta. In high school, you might have seen this construction here, where you come up with the height and then you compute, well, this is going to be sine theta times the actual base, and then that's the area of your parallelogram. So it's not very complicated to show that this is indeed the case. In general, though, the cross product is not associative, right? If you do the cross product of u with the cross product of v and w, that is not going to be the same thing as the cross product of u and v with respect to w. You don't even need to go to octonions, which we talked about when we talked about number systems, right? We can define something that behaves like a product that doesn't have a lot of the nice properties. that we would expect products to have based on what happens when we're just working with R. The example that you might use is that I cross K would be I cross 0. Don't just believe me. Actually go and compute K cross K. You can see it's 0, and I cross 0 is the 0 vector. But if you first compute I cross K, you will get minus J, and then minus J cross K, that's minus I. It's not 0. Again, you have to compute these things. If it turns out that U and V are parallel to one another in R3, then their cross product will be 0. Because if they're parallel, they don't actually build a parallelogram, and the area of the parallelogram here would actually have to be 0. The angle between them is 0, so the length of the U cross V is 0, sine of 0 is 0, and then you get a cross product which has to be 0. That's the only vector whose length is 0. But if they're not parallel, the cross product U cross V is one of only two vectors that are orthogonal both to U and V that have this very specific length here, the length of the parallelogram that's bounded by the vectors. So in physics, for sure, you use that to measure the torque. It's something like anti-commutativity shows up when you talk about elementary particles. And well, the right-hand rule is how you sort of remember how things work, right? If this is U, if your thumb is U and your index is V, then your middle finger points away from both U and V in that direction. One way to help with the computations is to remember that I cross J is equal to K, and then you can actually cycle through the permutations. The other thing that comes with this would be that J times K is equal to I, and that K times I is equal to J. And then if you want to reverse the order, remember anti-commutativity, K times J would then be minus I, and I times K would be minus J, and so on. Please take the time to verify that you can compute these things. I say take the time. It's going to be useful every once in a while, but this isn't something we're going to be spending an awful lot of time on. But you need to know how to create vectors that are perpendicular to one another, or perpendicular to two vectors, for sure. So how do we find normal vectors now that we have this cross product? It's not too difficult. You find two vectors U and V, which are non-parallel, so that the cross product is not the 0 vector. That cross product gives you a normal vector for the plane that contains both U and V. I just draw this here. Let's assume this is a plane. If U is here and V is here, then the vector that pops out at a 90-degree angle here, which is the normal vector, that vector is going to be parallel to U cross V. U, V, cross product pops up. So, can we find an equation for the plane that contains the three following points? 1, 2, 3, 1, 0, 0, and 0, 1, 1. It's easy for us to find two vectors, right? All we have to do is to subtract B from A and C from B, say. We get the vector 0, 2, 3, right? 1 minus 1, oh, I guess we did A minus B here. It doesn't matter which one we use. 1 minus 1, 2 minus 0, 3 minus 0, for sure. It's 0, 2, 3. And B minus C would get 0 minus 1, 1 minus 2, 1 minus 3. Oh, sorry. Again, I got the wrong one. I apologize. I was subtracting C from A, although this would also have worked. It would have given us a new vector, but the cross product would have been parallel. But I did write down B and C, so that'd be 0 minus 1 is 1, 1 minus 0 is 1, and 1 minus 0 is also 1. So BA and BC are these vectors. We could have used AB, we could have used AC. You could use any two of these four, would have been a good starting point. Now these vectors are parallel to the plane in question, so that's good. A normal vector then would be orthogonal to both of the vectors. So all you really need to do here to get a normal vector to that plane W is to find the cross product of these two vectors. Now, it's important that you notice or remember that you don't want to just use A, B, and C. A, B, and C are points on the plane. They're not vectors in the plane. Right? If I draw this here, say that this is the plane in question. If this is the vector A, well, A is a vector where I go from the origin to this thing here. That's not necessarily in the plane. But if I have A here and B here, then I could look at the vector between them, then that's definitely a vector that's in the plane. At least parallel to the plane when I scale it or translate it back to the origin. So we have the two vectors, BA, BC. We compute their cross product. You use the formula. I tell you it's -1, -3, 2. Don't just take my word for it. Make sure you know how to compute this thing. And that gives us then a normal for the plane. The normal is -1, -3, 2. So in the Cartesian form of the equation for the plane, we do -n times the vector x, y, z. So that would be -1 times x plus -3 times y plus 2z is equal to d. D, the constant term, will tell us the height of the plane. How do we find the d? We plug in any of the 3 points into this equation and we see what the value of d has to be. So if I plug in b, b is a good choice because it has a lot of zeros in it, then what I get is that -1 -3 times 0 plus twice 0 is equal to d, and that means that d is equal to -1. So the equation of the plane would be -x minus 3y plus 2z equals -1. You can use a combination of inner products and cross products to compute volume of boxes. I mean, it's sort of pointless in the sense that if you know the width, the length, and the height of the box, you can compute its volume, but sometimes the box is slanted or crooked and it might not be obvious what height would be in that case. So if you have 3 vectors, A, B, C, and these 3 vectors are, well, none of them are in the same plane, so we say that they're not coplanar. Coplanar? I don't know how to pronounce that word either, apparently. But if there's 3 of them and they're not in the same plane, they will bound a parallelepiped, which is like sort of the 3-dimensional equivalent to the parallelogram. Well, the cross product of 2 of them, U and V, although here I call them A, B, C, the cross product of U and V, and then the inner product of that with W, which is C, and then you take the length of that scalar, that's the volume of the box. And there's a proof here, which is mostly a visual proof. Visual proof, replace U by A and V by B and C by W, and then you will get the actual representation of this proof. So this thing here is called the triple product, or the scalar triple product, and it's a way to get a scalar value from these 3 vectors that are not in the same plane. So if you had to find the volume of the box whose sides were the following vectors, 1, 0, 1, 1, 2, 2, and 10, 0, 0, then you would first compute the cross product of 2 of them. And the order that you use here doesn't matter, but you compute the cross product of 2 of them. And then you'd get -2, -1, 2. Again, take the time to do this computation to be sure you get the same thing. and then you do the inner product with the third vector, the one you didn't use in the computation for the cross product, you get minus 20. You take the absolute value of this, you get 20. The volume of that box would be 20 units cubed. If it turns out that U cross V dot W is actually 0, what it's telling you is that U cross V is parallel to W, and so that the three vectors all actually lie in the same plane. You would say of these vectors that they are coplanar. They are linearly dependent, and this is a notion that we will revisit and use a fair amount in the rest of the course.